SnapMove, movement projection mapping in virtual reality. Can a virtual body control you? When embodying a virtual avatar in immersive VR, you control the body, typically, but when there's a strategic difference between where you see your hand and where your hand actually is, what's the effect on the user, and how can we leverage that in some way? I'm Brian Cohn, and I'll be presenting our research performed at Microsoft Research in Redmond, Washington. And this work was done at EPIC, the Extended Perception, Interaction, and Cognition Research Group. The paper I present today was researched by Antonella Maselli, Eyal Ofek, and Mar Gonzalez-Franco. Our paper achieves two things, but first let me give you some quick background. Today's objective is really going to be presenting the user study and then highlighting how we use it as an interface technique. So these are kind of two separate sections. So first, the rubber hand illusion shows how readily humans adapt to their hand's new appearance and location. But in a virtual world, we don't need superimposition of the real and virtual hands. There can be a disparity between the two. Take the go-go technique, for example. For positions close to the body, it's one-to-one. Your hand lines up with the avatar, but further from the body, the mapping switches to a higher order polynomial with distance, which multiplies your reach. Here you can see a video of reaching some things that are pretty far away that wouldn't be possible in the real world, but are possible with the go-go technique. Or similarly, ergo, which maps the real space to an interpolated, stretched mesh. So close actions are, again, one-to-one, but if you want to reach a further target up or to the right or in a less ergonomic space, it seamlessly blends those to make it possible to reach those targets. Or you can even move it so that it'll redirect your hand towards a desired target. And third, there's ownership, which was a study of ergonomics and body ownership when you rotate and elevate the virtual hand to right in front of the face, so it can be more ergonomic. So these techniques aim to reduce muscle strain, to maintain some body ownership, and often still have very high accuracy, even if you're reaching something across the room. But there is something about these that is the same, which is that for every position in the real world, there exists one position in the virtual world. SnapMove is very different. SnapMove is a many-to-one mapping, which means there are many ways to have the same virtual position. So here's what SnapMove is all about. While seated, we measure the shoulder position, and thereafter we collect the hand position in every frame. We get the distance from the hand's position to the estimated shoulder position, that's our reach distance, and then we apply that distance to a vector that goes from the shoulder to any direction, for example, in this case, M. So when you move your real hand side to side or up and down, the avatar's position remains in the exact same spot. But when you retract or protract your hand, the avatar just slides along the given projection line. In our experiment, we turn on SnapMove and then see what happens. And we see what people do during a repetitive reaching task that's in and out and backward. We change two things after SnapMove is enabled. One, we have conditions of different directions to move the projection line, different directions. Two, we quickly rotate the projection line away from straight ahead, or we slowly or gradually change it. So it's instantaneous and gradual. And then together that creates 8 conditions. Except for the straight condition is kind of the base case. So there's really only a straight instantaneous condition. There's no straight gradual condition. So as a result, we end up with 7 total conditions. Instantaneous or gradual onset, and straight, down, up, and side. 7 total conditions. And here's the experiment. We ask them to reach forward from a close point to a far point. After 2 short research, we turn on SnapMove, so the avatar hand will always fall aligned between those 2 points. Then, for each reach, we incrementally rotate the direction of that projection for each reach. And typically, whenever it's close to the body, that's when we change the direction. That way it's not super obvious far away at the hand. Every single participant drifted dramatically in many different directions in each of the scenarios. So here's an example of a down condition where it was gradual. And you can see that the tracking data, this is a side view, we have on the start, there's an evaluation of where that's where they first started, and then as the temperature gets closer to blue and from black, that's further on in the trial. This is what the straight condition looks like. You can see that there's no expectation of there's no change in the projection line, but underneath is where the real controller is. This is where we're seeing drift. And we're not even, in this case, we have kind of instantaneously a straight condition. And you see there's 2 controllers here. I'll get to why that is in just a moment. here's what they see, and this is an up gradual condition. They have to stay at the end. We ask them, hey, where do you think your real hand is? They make a guess using a plane they can control. Then we ask a question about embodiment, and then we repeat this a lot. So as a result, when you bring the hand up, it actually looks really weird if you use the same rotation. So we just rotate it about the disparity between the hand and the projection line. As a result, when you're holding the controller, if you go like this side to side or up and down or anywhere in between, that it looks as though the controller is completely steady. However, if at any position you slightly wiggle it, you'll see that wiggle in the virtual environment. So it really gets this really convincing feeling that it's actually in that right place. This is the code for the wrist rotation compensation. So our user study had 21 right-handed participants, 18 to 65 years old, mean of 29 years old. They were all free from any conditions affecting movement or control of the upper limb. And all their experience in VR was across the board. We had people who had never been in VR before, all the way up to VR experts. We had a good range. And here's some results from our 7 conditions, each repeated 6 times across different randomly ordered blocks for 42 total blocks, which took about 50 minutes for every participant. So in a very short amount of time, 16 reaches over 20 seconds, we measured the drift. And drift is the angle from the start point to the end point. It's this kind of like back and forth. So we get, every time you go there and back, we get a little angle to see how far you're going down. So it's the angle away from 0 for each of these reaches. So if they didn't drift at all, we would see over here the angle of drift stay at 0, which would be red. But in this case, you can see in the straight reach task, there actually is this drop, and very significant drop. So over the course of the trial numbers, they tend to pop down a little bit. That was what we saw in that video. And we have very interesting results for the other directions. See, the red line here is the avatar. If the black line matches the red line, the person is perfectly following the avatar. Notice how in the up condition, the drift seen in the gradual offset and the instantaneous offset are a little bit different. And notice how the instantaneous case, they quickly hit that level of drift and sustain it. And the same thing goes for the instantaneous case in the down condition and in the side condition. They don't continue to drift down. There's like this natural feeling of, all right, that feels right, and it continues. In the down condition, there's actually incredibly good matching. So once you've drifted down, that level of drift is actually equal to how much the avatars move down. So really it lines up very well when it's the down condition. And interestingly, in the side condition, which we were looking at from 2 sides, because we're looking at the vertical drift, but also how far they actually rotate, and in this case an external rotation from the shoulder, we actually see that there is a drift not unlike the straight condition down, in addition to that sideways. So they're going both, they're drifting down and to the right. But do they feel like their hand is in a new place? Well, we asked them to guess, where is your hand? So after every trial, we have them remain reached out. We'd say, all right, hold still. All right, guess where your hand is, then we'd do it this way. So this is kind of the experience. They'd use their other hand, rotate it to adjust the elevation of a platform. The platform would turn green when it stayed in the same spot after, you know, it kind of settled, and then they can click a button to lock in their guess. And we said put it underneath where you believe your hand would rest, as if it were like putting a table underneath your hand. And we did some calibration to make sure that was replicable. And we end up with this proprioceptive error. Do they overestimate where their hand is or underestimate where their hand is? On the x-axis here, we have how much they drifted away from straight movement. Each participant is a little dot on there. And when we asked them to do the proprioceptive quiz, like we asked, where's your hand? They were predictable in how far away their hand was. This indicates that the visual avatar is an incredibly strong visual anchor that biases the proprioceptive estimate. And you could really see that when you drift down, you overestimate your hand's elevation. And when you drift up, you underestimate your hand's elevation. So there's a very strong relationship here, which is very significant for all of these cases, but not for the up condition. Interestingly enough, the up gradual and up instantaneous did not hold this relationship for proprioceptive drift and the physical position drift. So Then let's talk about embodiment, because proprioception and movement and embodiment are all interrelated in different ways. So after every trial, we would quiz them and ask them, did you feel embodied? And in this case, we used these 3 questions pulled from the literature on a Likert scale to ask how embodied they felt with the virtual avatar. And using these questions over the course of many iterations and kind of squishing it together, we end up with values for a given person. To make it comparable between people, we compute a z-score for each person for each question that represents their relative intensity of embodiment. So if they put everything in the very high range, it would still work. And so we took those embodiment answers, compiled the z-scores, and showed that the up condition is the least embodied type of condition, and the down condition is the most embodied condition. Looking at the far right, we see that across the board, a gradual onset is the best way to really lock people in and to get the higher levels of embodiment. So if you're going to move people, do it gradually and ideally down or to the side as opposed to up. And here are some of our user study findings. So first, participants are converging towards the avatar in both gradual and instantaneous conditions. There's more movement towards the avatar, inversely proportional to the proprioceptive drift. And the level of embodiment depends on which direction you go. The proprioceptive drift is related to how far the individual drifted. And finally, the up direction had a weaker effect, meaning there's a trade-off between fatigue and possibly minimization of sensory conflict. And so let's get into some applications for this work. We extended this to climbing, for example. So someone who can't really reach above their head could actually play a climbing game with very small, like in their lap kind of movements. So you look up and see the target and reach to it. And unlike in a situation such as ownership, which would, you'd have a one-to-one mapping between your hand down here and your hand up there. In this case, we could lock it actually directly to the target. So all you have to do to hit the target is just reach your hand forward, and you have this kind of feeling of grabbing it, but even though your hand is down lower. Similarly, we were able to make people feel like they could throw really well. It's kind of like an aimbot, where if you're throwing a dart and throwing them over and over again, if it was just that you threw it and you'd see the dart twist, or it would just come out of your hand in a different trajectory than you threw it, it'd be very obvious that you're not actually getting good throws. But because we're projecting the whole hand and arm, it appears as though it's a perfect throw. You feel and see a perfect throw, and you see yourself in the right posture for it. So it really is convincing. And my favorite demo is this rowing your boat experience on the water.
Sometimes, manipulating a virtual object can take up a lot of real space. We extended SnapMove to projections onto a plane, allowing virtual movement to be large, while the user is stuck in a more restricted space.
With our demos of climbing, throwing, and rowing, we're not saying that SnapMove is the best way to handle these problems. If you want accuracy, the earlier techniques are probably a better fit. But if you want to manipulate the way the user moves, SnapMove is an interesting way of doing it. And it's a creative way to explore these kind of neurophysiological pathways, visuomotor loops, and the interplay of movement, embodiment, and proprioception. In the future, we want to leverage SnapMove as a means of retargeting towards new targets, maybe even haptics. There's opportunities to combine SnapMove with things like GoGo and Ergo and ownership. And also there's an opportunity to evaluate with participants who have a movement disability, such as essential tremor or cerebral palsy. And so for today's objectives, we've gone over the user study, and we've highlighted how SnapMove can serve as a new 3D user interface technique. Thanks. If you're interested in any more of this work, you can go to briancone.com, and I'll put some links to our work on Microsoft there.